Have you ever tried to learn something really complicated, like maybe playing a new piece on an instrument perfectly? But imagine the only feedback you get is right at the very end, just a simple yes or no, success or failure.
Yeah, no hints along the way, nothing.
Exactly. Just one big pass or fail. It's incredibly difficult, right?
Oh, absolutely.
Well, that's actually a pretty familiar struggle for robots and AI.
Yeah.
Especially when they're trying to master these complex tasks with, lots of steps. And that success signal only comes in the very, very end.
It really is. It's a classic persistent challenge in AI, particularly in reinforcement learning, or RL as we call it.
Right.
And for this deep dive, we're actually unpacking a new research paper. It's from UC Berkeley, titled Reinforcement Learning with Action Chunking.
Okay, so action chunking. Our mission today, then, is to really understand how this paper tackles, well, one of the big problems in RL, specifically in this thing called the offline to online setting.
Yeah.
See, it's just really tough for RL agents to explore efficiently from scratch.
Yeah.
Especially when the rewards are sparse. Like, they don't get feedback very often. And it's even harder to use existing offline data, the data collected beforehand, without introducing some kind of bias.
Yeah, that bias is a killer.
And here's where it gets really interesting, I think. Think about how we, as humans, we're constantly leveraging our past knowledge, our experiences, right, to learn new stuff.
Totally.
But for an AI, doing that effectively from a collection of past actions that might not even be perfect or, consistent, that's actually a huge hurdle. So, what are some of the typical ways that trips up traditional RL agents when they try to just use that past data?
Well, that's precisely the challenge, isn't it? And it's not just about misalignment. Sometimes that old data is just, too inefficient or maybe incomplete to really guide the online learning effectively. So, traditional methods can easily get stuck just trying to perfectly imitate maybe suboptimal or even irrelevant past actions. And that leads to really slow progress when they actually try to act in the real world, online.
Right. They get stuck in the past, basically.
Exactly. And this is where the paper's promise really comes in.
Okay. Sounds like they might have found a significant leap forward then.
Yeah.
They introduced something called Q chunking. You said it's a surprisingly simple yet powerful recipe that promises to make RL much more sample efficient and effective for these really tough, long-horizon, sparse reward tasks.
That's the claim, yeah. A simpler recipe for better learning.
Okay, let's unpack this core idea then. Q chunking. You mentioned it's heavily inspired by a technique that's popular in imitation learning, which is a slightly different area where agents learn by watching demonstrations.
That's right. Imitation learning, or IL.
So can you tell us more about action chunking itself? What is that?
Sure. So in imitation learning, action chunking basically means that instead of the system predicting just one single action at a time, like, moving one tiny joint on a robot arm, it predicts a whole sequence of future actions, an entire action chunk.
Ah, okay. A sequence.
Yeah. And this approach, it's become quite popular in IL, mostly for its robustness and also its ability to handle what's called non-Markovian behavior.
That's fascinating. Non-Markovian behavior. Okay, for those of us who might have heard the term but aren't totally sure on the practical side,
Yeah.
what does that really mean for, say, a robot? Maybe you could use a dance move analogy.
Yeah, absolutely. Non-Markovian basically just means actions that don't just depend on the immediate current state, right? They depend on a longer history or sequence of previous actions.
Right.
So think of it like that dance move. You don't just predict one tiny muscle flex. You predict the sequence of movements that make up the whole step, A pivot, maybe a slide, then a dip, that whole sequence.
Gotcha. It depends on what came before, not just right now.
Exactly. And the surprising thing is action chunking wasn't really widely used in traditional RL before this paper because, for a long time, the thinking was that optimal policies are usually Markovian.
Meaning the best next action only depends on the current state.
Precisely. So people kind of thought, chunking might be unnecessary, maybe even suboptimal in RL. What do you think made researchers so convinced of that Markovian view for so long? And what kind of shifted things?
That's a great question. It's almost like a philosophical thing in AI, isn't it?
Yeah.
I guess the conventional wisdom was probably rooted in a mathematical neatness of Markov decision processes. They're just cleaner to work with.
Mathematically convenient.
But then the sort of aha moment in this paper seems to be the observation that, the final optimal policy might be Markovian. The exploration problem itself, that really difficult initial learning phase where the agent is just trying to figure things out, That can be tackled much better with these non-Markovian temporally extended skills.
So the learning process benefits, even if the end result looks Markovian.
Exactly. And action chunking provides a surprisingly simple way to get that benefit. So how does it actually work then in Q chunking?
Okay, so Q chunking essentially runs the reinforcement learning process, but it does it in this chunked action space.
Okay.
This means the part that decides what actions to take it, predicts a sequence of H actions. H is just the length of the chunk.
Right, the number of steps in the sequence.
Exactly. And that's the part that evaluates how good those actions are. It considers the value of the entire sequence of H actions, not just a single one.
Interesting.
It's like asking, what's the value of doing this whole dance routine? Not just, what's the value of this one tiny step?
So it's not just about doing one thing well, but understanding the value of a whole mini strategy almost. That makes a lot of sense, actually.
It does, right?
So what are the main upsides then? What are the core benefits of doing it this way?
Well, the paper highlights two core benefits. The first one is all about efficient value, backup, and stability. We could maybe call it skipping time steps effectively.
Okay, skipping time steps. Now, just to give a bit of background for everyone, temporal difference or TD-based RL, which is, super common.
Very standard.
Agents learn the long-term value of actions by kind of comparing their current prediction to a slightly more updated one for the next time step, the sort of bootstrap. And they gradually improve their estimates. This whole process is often called value backup.
Right.
Now, a common trick to speed this up is using n-step returns, where you essentially look ahead in steps into the future to calculate the value, not just one.
Yeah, that's a standard acceleration technique. But the problem with standard n-step returns is that they often run into this biased value estimation issue, especially when the data you're learning from is off policy.
Meaning the data wasn't generated by the agent's current strategy, but maybe from an older one or a totally different one, like human data.
Exactly, and that mismatch can make the value estimates inaccurate, which, really slows down learning or sometimes even stops it from working altogether.
Okay, and this is where Q chunking comes in strong.
This is where it really shines, yeah. Because it uses a Q function that takes the entire action sequence, each steps into account, it completely gets rid of this bias. Completely eliminates it, while still getting that H times speed up in how fast the value information propagates back.
Huh. So it's like having your cake and eating it too for learning speed and accuracy.
That's a perfect way to put it. It's not just a small improvement. It really tackles a core dilemma in RL. It lets agents learn robustly from diverse data, even off-policy data, while still getting that accelerated value learning. That's a major step forward for actually using this stuff in the real world.
Okay, that's a big one. What's the second core benefit?
The second major benefit is about effective exploration, specifically getting temporally coherent actions during exploration.
Right, because in these complex RL tasks, just trying random stuff is super inefficient. Like you said, a robot just flailing its arm randomly, hoping to hit a target by chance.
Exactly. Total waste of time, usually. And also, as we kind of touched on, that offline data, maybe from humans, maybe from older scripted policies, it can be non-Markovian. It has that sequential nature. And that makes it tricky for traditional RL methods to really use properly because they're often expecting single independent steps.
That makes sense. Yeah, like if human demonstration isn't just separate snapshots, it's a fluid motion, right? A whole sequence. So how does Q chunking make sure it doesn't just look fluid, but actually captures the underlying skill or intention?
Well, it does this by imposing a behavior constraint on these extended action sequences, these chunks.
It's a constraint.
Yeah, basically guiding the learning process. This encourages the agent to learn temporally coherent actions. You can think of these as more natural extended skills, like, say, consistently moving in a certain direction for a bit, or performing a whole jumping motion to get over something, rather than just a series of jittery, disconnected, micro actions.
So it encourages smoother, more purposeful movements.
Exactly. It's about encouraging the AI to move with intent, you could say.
And why does that structured, purposeful exploration help so much with finding those sparse rewards faster?
Because it just leads to much more structured exploration overall and better state coverage, meaning the agent actually visits more relevant parts of the environment.
Right. It's not stuck wiggling in one corner.
Precisely. It's not just flailing randomly. It's performing more meaningful multi-step actions. And that helps it stumble upon those rare rewards much, much faster. It's actually a surprisingly simple way to sort of extract skills from data without needing all the complexity you often see in, say, hierarchical reinforcement learning, where you have layers of policies managing sub-goals.
Interesting.
So yeah, essentially, they seem to have found a kind of shortcut to building more intelligent exploration behavior without the usual architectural headaches, which, for anyone trying to implement this stuff, that's a dream.
That really is a powerful claim, simplicity leading to these big benefits.
Yeah.
Okay, so these ideas are great, but how do they actually turn into algorithms, into code? The paper talks about two practical algorithms from this Q-chunking recipe, QC and QCFQL.
Right, so QC first. That stands for Q-chunking with implicit KL behavior constraint. It uses a technique called best of N sampling.
Best of N?
Yeah. Basically, it samples N different possible action chunks from a learned behavior policy that's a policy trained to mimic the patterns in the offline data. And then it just picks the one chunk out of those N that the current Q function predicts will give the highest value.
Ah, okay. So it generates a few options based on past behavior and picks the best looking one.
Exactly. And that best of N part acts as an implicit constraint. It subtly nudges the agent's new learning towards behaviors that are kind of similar to the good stuff already seen in the offline data. It stops it from just wandering off into totally useless actions.
Okay, that makes sense. And what about the other one, QCFQL?
So QCFQL stands for Q-chunking with two Waterstein distance behavior constraint. It's a bit more mathematically involved, but this one uses a different framework called optimal transport.
Optimal transport. Sounds fancy.
It is a bit, yeah. But the core idea is that it helps the AI adapt to that reference behavior, the offline data, in a really smooth and robust way. Even if the old data isn't a perfect match for what the agent needs to do now, it's kind of like finding the most efficient way to morph one distribution of behaviors into another.
Okay, so different math, same goal. Stay close to the useful prior data.
Pretty much. And what's really neat, they emphasize, that both of these are actually simple to implement, and you can run them directly for offline RL pre-training, which gives the agent a really strong head start before it even interacts with the real environment, boosting that sample efficiency even further.
Pre-training is always good. But the proof is always in the pudding, isn't it? The results. They tested Q-chunking on some seriously tough environments you mentioned. Where exactly did they put it through its paces?
They did. They used OGBench, which has 5 different domains, things like puzzle 3x3 sparse, and then various cube manipulation tasks, cube double, triple, and even quadruple.
Cube quadruple, that sounds hard.
Oh, yeah. And they also used RoboMamic, which has tasks like lift, can, square. The paper describes these as long horizon, sparse reward, robotic manipulation tasks. And to really give you a sense of the difficulty, they explicitly note that cube quadruple is extremely difficult to solve from offline data only.
Extremely difficult. When I hear that, I just picture a robot arm kind of giving up and having a little tantrum. Like, what does extremely difficult actually mean in terms of, say, failure rate or compute needed?
Yeah, you can imagine. It basically means these tasks are often just intractable with many standard methods. You might need millions, maybe even billions of attempts to get any success if you get there at all using only offline data. It's the kind of problem that really pushes you to think, okay, there has to be a better approach.
Right. So how did Q-chunking do? What was the overall performance?
Well, Q-chunking, both QC and QCFQL, achieved what the paper calls strong performance. Often, it matched or even beat the previous state-of-the-art methods designed for this offline to online setting.
Matched or beat. That's significant.
It is, and this was especially noticeable in the online phase of learning when the agent actually starts interacting with the environment after pre-training. It showed really significant sample efficiency gains on the hardest tasks, like those cube ones.
So learn faster in the real world, essentially.
Much faster, yeah. Imagine that robot learning to stack 4 cubes correctly way quicker than previous approaches could manage.
That's incredibly impressive.
Yeah.
Okay, but this raises a key question, right?
For what?
What about methods that maybe use that in-step return idea to speed up learning, but don't use the chunked critics or policies? Did they get similar benefits just from looking ahead?
Great question. And no, not at all.
Really?
The paper's experiments specifically included these baselines, and they performed significantly worse, sometimes even worse than simpler one-step methods. Yeah, so that really highlights that the magic isn't just looking multiple steps ahead. The benefits of key chunking really seem to come from operating in that temporally extended action space itself. It's the chunking part that's making the crucial difference.
Okay, that's a very clear result. Now, you mentioned earlier it leads to better exploration, but People might wonder, how do we actually know it explores better? They can't just tell us, they need to show us something, right?
Exactly, and they do. The paper includes visualizations of the end effector movements, basically, tracing where the robot's gripper or tool moves early on in the training process.
Ah, okay. Like drawing its path.
Precisely. And Q-chunking's trajectories, compared to other methods, they have noticeably fewer pauses. They look smoother, and they achieve more diverse state coverage.
So it moves more fluidly and covers more ground.
Yep. It confirms that it seems to be moving in a more fluid and purposeful way right from the start. They even quantify this using temporal coherency measurements, which basically means they mathematically measure how smoothly and continuously the robot is moving. It's pretty compelling evidence, I think.
That is compelling.
Okay.
And for some practical insights, they did a sensitivity analysis, right? Looking at how changing different settings affects performance. What did they find out about things like the chunk length?
They did. For the chunk length, they found that while making it longer generally helps, the benefits didn't seem to drastically increase much beyond H5.
Okay, so 5 seems like a sweet spot.
Yeah, kind of a good balance between benefit and computational cost, which is super useful if you're actually trying to implement this.
Definitely.
They also looked at the critic ensemble size, using multiple critics to stabilize learning. They found that using more critics, say 10 instead of the default 2, can improve performance sometimes. But the default of 2 still worked remarkably well across the board.
Good to know the default is solid. Anything else surprising?
Yeah, one thing was a bit surprising. They looked at the update to data ratio, or UTD. That's basically how many times you update the model for each new piece of data you collect online.
Right. Sometimes cranking that up helps sample efficiency.
Exactly. But here, they found that increasing the UTD didn't necessarily improve sample efficiency much for Q-chunking, which is interesting. It suggests Q-chunking is maybe quite robust and doesn't need excessive updates to learn effectively from new data. Another practical finding for people implementing it.
Huh. Okay, so wrapping this up then, what does this all mean for the bigger picture? Where does Q-chunking fit in?
Well, I think it offers a really simple, yet, as we saw, remarkably effective recipe. It tackles one of RL's really tough challenges, how to learn efficiently in these complex, sparse reward environments, especially by leveraging prior offline data effectively.
So that offline to online jump.
Exactly. And it does this by combining those two key ideas we talked about, speeding up the value learning without introducing that nasty bias, and promoting more intelligent, more structured, temporally coherent exploration, getting those skills out.
Yeah.
So overall, this work feels like a really significant step towards training these non-Markovian policies specifically for more effective online exploration. It's genuinely pushing the boundaries of what RL can achieve, especially with real-world, messy data.
It really sounds exciting. And it leads to thinking about the future, right? The paper used a fixed chunk size, RH. But what if? What if an AI could automatically figure out the best chunk boundaries, like maybe short chunks for fine motor skills and longer ones for navigation, or even learn more generalized, flexible, non-Markovian behaviors completely on its own?
Ooh, now that's interesting. Adaptive chunking. Imagine the kinds of complex, really fluid actions robots could learn then. They wouldn't just be playing back sequences. They'd be genuinely creating and adapting novel, efficient ways of behaving on the fly.
The potential seems huge. So, a final thought for you, our listener. What stands out to you about how this kind of approach thinking, in terms of action sequences, not just single steps, could change how we teach AI, or even how AI learns complex skills in the future?